In this video, we want to have a better new definition for jointly normal distribution. So in this redefinition, we say that a set of random variables are normal or jointly normal if any linear combination of them has a normal distribution. Mathematically, if you have this definition is self-sufficient because normality is defined here using the same definition. So which one we need is like a chicken and egg. So normal distribution, the definition itself needs inside itself a definition, but we are not going to, because it's going to be a little bit complex. You can do it, it's not very hard, but we're going to make a easier shortcut. So the distribution of the y in terms of distribution x in terms of the PDF is complex, but in the characteristic domain we had a simple relationship that a characteristic function of y can be written in terms of characteristic function of x. So if you use characteristic function of x, but instead of its frequency you put omega a, you get characteristic function of y for omega. But this definition is valid for all a. So I could vary a and then prove that these functions should be, the log of these functions should be a second order polynomial and so on. But I'm not going to do that. I'm going to make a shortcut. So we want to prove that if this definition is valid, the only characteristic function acceptable is of this form. So that means that logarithm of these is a polynomial of second order in terms of omega. And if you take multidimensional inverse Fourier transform of that, you get this one. So basically, this definition will lead to this joint PDF or this joint characteristic function. And this notation is determinant. So determinant of the covariance matrix, this is the mean vector, and so on. So you can prove that. So I leave the proof to you. A zero mean normal random vector. So if in the previous definition, if you replace mu x is equal to 0, then it will simplify. If you put omega equal a, the random variable w omega transpose x will have a normal distribution. This is obtained from the definition. And then from there, we get the characteristic function of these will become equal to this one. So sigma 2w is something to be calculated. And we also have that variance of these because this is w to the power 2. Remember that here the random variables are real. For complex random variables, we don't define characteristic function like that. We need something else that I will not consider it in this course. It's not complicated, but you can first concatenate the real part, imaginary part together, and then define the characteristic function. That's okay. Otherwise, you will not get the correct results. So the variance of these can be calculated, and now if you put back these here, then you get your proof complete. So what you see is the characteristic function of w at 1 is going to be equal to this one, and then this gives you the characteristic function of omega. And basically, by inverse Fourier transform, you will obtain this one. So if you follow these steps, you'll see that this is a complete proof, except that I assume that the means are 0. So the implications of this theorem are very interesting. So if you have a bunch of jointly normal random variables, then any moments of them can be calculated very easily using the characteristic function. For instance, if you want to calculate mean of x1, x2, x3, x4, there is a general simple rule that you could say, oh, because I have 4 terms, I can take them 2 by 2. If I take these 2, I get covariance of C12. If I take these together in here, then I have to consider x3, x4. So this is what I have. Now, all possible combination, because I can take x1 with x3 and x2 with x4. So this, I get these terms. Or I can get x1 with x4 and x2 with, I get this one. Now, for this case, if I have 6 of them, what I get? I have to get these 2, so it's going to be equal to mean of x1, x2. Now, I get mean of x3, x4, mean of x3, x4, and then a mean of x5, x6. Now, plus all possible such combinations 2 by 2. Okay, the reason is that if you look at either the joint distribution of normal random variables, or if you look at the characteristic function of, let's say, x of, let's say, omega is only a function of expected value mu x and cxx. Okay, now if they are 0 mean, mu x is 0, so you have cxx and so on. So if you for instance, if you want to calculate this one, characteristic function phi x of omega is equal to expected value of e to the power of j omega 1 x1 plus omega 2 x2 plus etc. Now, if I calculate derivative of these with respect to omega 1, what will happen is that this x1 will appear here. So if I add derivative of these with respect to omega 1, I'll get x1. If I calculate, because I have x1, I want x2, I calculate derivative with respect to omega 2, I'll get x2. If I want x3, x4, so I have to add these ones and size. Now, once I have these 6 partial derivatives, I replace all omega i's, omega 1, omega 2, etc. by 0. Then this becomes 0, and then e to the power of this. So this disappears, and I get this expression. So what I need to do is to calculate the derivatives of these joint characteristic function with respect to omega 1, omega 2, omega, etc., and then replace them by 0. And then if you do that, you will obtain these rules, that 2 by 2 rules. So moments of a 0 mean normal random vector can be easily calculated using that, because if you have this expression, okay, so what you could do, you have e to the power j omega transpose x, and then you know that e to the power a is equal to summation of a to the power of p divided by p factorial, and then p from 0 to plus infinity. This is Taylor series expansion for exponential function. So this a is equal to j omega x. So this is a. So if you compare these ones, so e to the power of jm is that. So expected value is there, and I put. So if I use that, then I get this expression. Now I have this guy, and j to the power of p is equal to. You could expand it. You could take this expectation inside a summation. And what you see is that you get this expression. So you can simplify a little bit. So you can now we could also expand the formula for the characteristic function. Now this is also e to the power of a, so you could use that, and then you get this expression. So this expression, this one simplifies. So this is a series expansion, and then you have moments of this guy, and here you have another series. So this is a function of omega, this is another function of omega, both of them are series. So these two guys are equal. So the coefficients of this is like a Taylor series expansion in terms of omega, and this is also a Taylor series expansion in terms of omega. So equating these two guys, you will find the same rules, and from there you will because omega transpose x to the power of 2p is going to be this one. So I'm here expanding this guy, and this guy should be equal to that, the same coefficients. So if you equate that, then you will get the rule that I'm talking about. For instance, the coefficients of omega 1, omega 2, omega 4 gives you the proof of the first case, and then the coefficients of omega 1, omega 2, omega 3, omega 5, 6 gives you the next one when you replace everything.